So I have all the quiz questions, right? So what's the answer for the first one? A single-threaded process running on a multiprocessor machine. Do you worry about critical section? In a single-threaded process running on a multiple processor machine, yes?
No, because it can only run on one processor anyway.
Yeah, so it's only one. There may be multiple processors, but from a process perspective, which is what we're concerned about, right? It only has one thread. So one thread cannot, one thread by definition will always be inside the critical section, right? Remember the three conditions. One of them is only one thread can be inside a critical section. Since you have only one thread, the point is mute. We don't have to talk about anything, right? And what about the next case? If you are in a single processor machine with multiple threads, yes?
Not true, because you can still get the instructions interleaved between different processes.
Yeah, it's true, because even though two threads cannot be inside the thread at the same time, but virtually speaking, one thread could be context switched out halfway through, while the other ones can be running, right? Context switch can make it look like two threads are inside the same thing, right? So you would still have the same problem, because one thread may be working halfway through, gets context switched out, another thread comes in, and that can cause a critical section violation, right? So, and this segment of code, right? So it's supposed to show that there's a critical section here, but you're also modifying something outside the critical section, right? What would you get? Do you get a segmentation fault, or illegal data access in thread 2 fault, or critical section violation error, or none of the above? How many wrote A? How many wrote B? I have 1 for A, 2 for B. How many wrote C? 4 for C. How many wrote D? Oh, it's like a 1 versus 100 kind of thing, right? Many people voted for D, right? The answer is D, right? Mostly because remember, critical section is something that you are supposed to use as a programmer to do something. Operating system does not care if you write buggy code, right? That's true throughout the whole process, right? Operating system's job is not to make sure that your program is not buggy. Here, you didn't define what a critical section was and accurately for whatever reason that you decided, right? So from an operating system perspective, it does not know what you do inside. It does not keep track of what variables you're doing. It's not doing a program analysis. It's not trying to figure out what is essentially changing, what is doing all the stuff. All it knows is you said the critical section here, you said something else here. It only promises that only one thread can be inside this section. It makes no promises on code analysis, right? Because to do this, somebody has to analyze the code and find out that you're using a variable here called count, and that's potentially being used somewhere else, and that could potentially be problematic, right? If you take a course on computability, theory of computation, one of those things, right? You will realize that this is impossible to do, right? It's impossible for a program to analyze a program to see and tell you exactly whether the behavior of what it can do, right? It can only do heuristics, but it can't really do that anyway. So operating systems don't attempt to do that, right? It's anyway the job of the compiler to generate the code and stuff. All it knows is if you said critical section here, critical section here, anything in the middle, only one thread will be running. What you do in there is your business, right? And if it turns out that your program tends to be buggy, you get bad results, right? You get none of these errors. Right? And as we go through different stuff, when you talk about memory and all those things, there are some things the operating system will tell you. There are other things it's up to you to figure out whether something is wrong and deal with that, right? Does that make sense? Okay. Sorry. Yes, I still need you to pick up the, especially the quizzes, because I don't have the name for one person, but I think 3 or 4 people did not take it. So I can't even give the grades to that one person by induction, right? So you have to show up and figure out, claim that one name, right? I think that person got a 2, so more motivation. If you did the quiz and your name, you don't have a grade, then you get a 2, right? So all right, so do you have any questions about critical sections that we covered so far? What we covered so far is the notion of what a critical section is and what the promises it will give you, and some of the ways you can implement that, and especially if you had access to hardware like test and set or swap, which tells you precisely what is how to write the code around that, right? Where we left off was this notion of a semaphore. Mostly because as a programmer, you adding these code, right, adding these instructions, which are hardware instructions, and making sure that everything works fine, is considered to be very hard, right? How many of you started your homework project 2? At least you should start thinking about what the program does and how you may try to do the stuff, right? And you realize that writing the code may not be as trivial as you imagine, because you have to kind of understand how these things work, right? So some of the abstractions that people have come up over the years is what we'll look at next. Essentially, these are supposed to make using the critical section parameters easier for a normal program to use, right? And in the quiz or in the abstract, when they say begin critical section, end critical section, these are the constructs that will kind of delineate what is a critical section. The first one is the notion of a semaphore, right? And semaphore defines 2 operations. One is a wait and another is a signal, right? And it could be a binary semaphore, which is traditionally called a lock. And traditionally people call the critical section as a locked piece of code, right? So if you're inside, you call it locked, right? Because there's only one thread can be inside. And practically, if you set the critical section values to be 0 or 1, then it's a binary lock. Then only either of 1 or 2 threads can get in. But you can also implement this as a semaphore of value n, where any one of n threads can go in, right? So the way up to n threads can be inside the lock, right? The way you define that is if you have a wait operation. Again, these are atomic operations, so you cannot split them. Atomically, if you do a wait, it'll decrement the count and go on till it gets to 0. And then it'll go into a busy wait, or this is called a spin lock. If you say while s not less than 0, you do nothing, that's called spin lock, because your processor is spinning on that variable, right? It's spinning on s. As long as s is true, you keep spinning, right? So on the signal side, when you exiting, so this is the traditional what is used to define beginning of a critical section. This is for the end of the critical section. At the end of the critical section, before you leave, you signal it, meaning you increment it. So some of the threads which are waiting, one of them will succeed, because one of them, when they're going through the loop, one of them will succeed, and they get to run, right? And the way you use that in typical programs would be if you have 2 threads and you have some statements which you want to be inside a critical section, you would want to, the begin critical section would be a wait, and then the exit would be a signal, right? So in the first one, if you say wait, then till somebody signals it, you cannot enter, right? And that's one way to make sure, to control how many threads can be inside, right? So if you have a thread number to be more than, semaphore number to be more than 1, if you initialize it to more than 1, then you can potentially have more threads going into the system, right? But not no more than n, right? And this is one program code that you would probably find it useful in your example to use for your system, right? And the challenge in implementing that was, we saw the little piece of logical code. In practice, you have to make that the spin lock wait you have to implement some way to say if your semaphore is going to 0, that the next thread which comes in has to wait, right? And the way we made it wait in the previous slide was to do a while loop. That's called a spin lock. And if you do a spin lock, that means you are consuming CPU, right? So that thread, whatever CPU is assigned to it, you'll continue to use that much, right? So from an operating system perspective, you don't know what this thread wants. You know this thread is always ready to run, and you have to give it the CPU, and it has to go use its entire clock cycle, right? And that's a waste because you assign each processor a certain amount of CPU cycles, and you don't want it to waste it by just going through a spin lock, especially on a single processor machine, right? If you're on a single processor machine, like we asked in the quiz, it's possible that there are multiple threads. It's possible that one of the threads got scheduled. So when it is running, there is no possible way that the variable could be set, right? Because you have two threads, but because there's only one processor, only one of them can be running at any one time. So the first thread will be in the spin lock for its entire life cycle. And then when it gets context switched to the next one, then the next one can make progress and call signal, right? So spin lock makes no sense on a uniprocessor machine because you end up wasting the CPU, and you can probably argue that you always waste and never get what you wanted, right? So if you don't want to waste your CPU, you have to find other ways of implementing this. You don't want to spin lock and wait. So we'll see one of the ways you define is you define a notion of telling the operating system that I'm going to go to sleep, block me till somebody can wake me up, right? So you define a queue, and you define a virtual queue where application can voluntarily give up its CPU. You can say at this point, I'm going to go to sleep, and somebody else should wake me up, right? And we'll see how that works in the next section. But before we go, so the other way to do that is also to disable interrupts on a single processor. In a single processor, you may think about disabling interrupts. But so again, going back to with no busy waiting, you define two new operations called block and wait. And you use the block to say if a thread doesn't see that it can be scheduled, it blocks itself, and somebody else has to wake itself from the signal thing. So this is how the logical program would work. So again in wait, if value is less than 0, right, rather than going into a while loop and waiting for S to change to something 0 or above, you call block, right? That means the thread which is running wait will voluntarily make a system call called block, which means that your process the thread will be moved from, if it's a kernel level thread, will be moved from running to wait state, right? It's waiting for an event which is not an I/O, but an event which will be released by wake up, right? So one of your threads has to do a wake up. So when it does a wake up, your thread is moved from wait queue to ready queue, right? So this is another way of you scheduling yourself, another way for you to not wait for I/O, but wait for some event which is happening within your process. And in signal, you increment the value, and if you find that you increment the value to be above 0, potentially some thread could be woken up, so you call wake up, right? And it's up to the operating system to figure out which one of the block threads should be woken up. It's not saying wake up that particular thread. If there are more than one thread waiting, one of the thread will be woken up, right? So this is a way for you to voluntarily work with the operating system to get some services. And we'll see that in some other context too, right? Where if you as a process or a thread know that there's nothing much you can do, you voluntarily give up the CPU because that's a good way to be nice to the entire system and to make progress, right? And again, this all depends on you doing this stuff voluntarily, right? Whoever implements the threads, the Semaphore did not have to call block. They can call it as a while loop, right? So the good reason of why you would do a block is because if you know that you're a single processor machine, you're not going to get the CPU. Why not just give up so you can make progress, right? What's the bad point of using block? Why would you not use block? Why would you spin rather than block? I'm not arguing whether it's single processor or multiprocessor, but what is potentially the good thing about a block, spin compared to a block? Yes?
Context switch?
Yeah, so when you have to call the operating system for anything, you have to context switch, right? So these are, however small the overhead is, it's still an overhead, right? So on a single processor machine, it makes no sense. On a multiprocessor machine, you do hope that some other thread and some other processor would be able to finish its task and give control back to you. So you are willing to waste the CPU a little bit more because you know there are more than one CPU anyway. So, but you hope that somebody can make progress and give it back to you, right? Because when you call a block, that means you are put in the wait queue, right? So when somebody calls a wake up, you don't immediately become runnable, right? From block means, so when any thread which is blocked would move from the wait queue to the ready queue, right? And then it'll wait on the process scheduling or thread scheduling stuff. So if you're doing a first come first serve, then you have to wait for your turn again, right? So it's potentially not only the overhead of context switching, it's also the overhead of you have to wait again to get back into the system, right? And that could potentially be tens of milliseconds, right? So if you expect the spin to only happen for a few milliseconds, you're willing to waste the CPU and keep going, right? And especially on a multiprocessor machine, this is true. So if you're in a multiprocessor machine, typically you tend to spin rather than do the block and stuff. Even though, even on a multiprocessor machine, it's still a good thing to do for the overall system, you as a program may not want to do this stuff, right? You may want to spin and not give up the CPU, right? Because you have to look out for your own good too, yeah.
I'm sorry, what exactly do you mean by spin?
Spin is that while nothing. It's called a spin because it's if you think of the program logic, it's basically spinning on that one variable, right? It's spinning, waiting for the variable to change value, right? If you're saying while s equals 0, then you're spinning, waiting for s to become 1. So it's called the spin lock, right? Yeah, so that's the challenge between using the spin lock and the blocking lock. And we'll see that throughout the system, because there are cases when you know something is up, you can be nice by giving up your CPU, but you have to weigh it against what your overall goal is. You don't want to be so nice that you end up doing good for the system, but your own performance goes bad, right? So in this case, if you call block too often, then your performance would be really awful. Overall system would be good, right? There are other ways of doing this. One is a conditional variable, which is a lot similar to your semaphore. You define a variable as a conditional variable, and you define a notion of a wait and a signal. And so whichever calls a wait is stopped, and then a signal would wake that particular process up, right? So when you look at the pthreads library, it has a notion of semaphore and conditional variables, and each of them provide different ways of doing the stuff, right? One thing to remember in all of this stuff is you still have to know what is the beginning of the critical section, what is the end of the critical section, right? So that means you can get much more finer grained control. For example, in your matrix, the operation for your homework project 2, you really want as close control as possible, because the closer control you can do, if you notice there are some operations which don't have to be locked, you may let them go, right? So if you know like that this row is never modified for a certain set of operations, you don't have to lock them, right? So it gives you more power, but it also makes writing the program a little bit harder, right? Next, we'll see some other abstractions which are designed to make it really easy, where you don't have to worry about anything, right? The penalty you pay for that is it does not give you the fine level of control, right? One such code construct is called the monitor, right? Essentially, you define a whole function to be a monitor. That means this function, if you call a function a monitor on something, right? So you have to say what variable this is monitor on. So if you have two functions which are monitor on the same monitor, then only one thread can be into one of the function, right? It's the same as you writing a semaphore, critical section begin and end for the whole function. So for example, if you have a program like this, ignore the monitor construct, right? What you really want is if you want only one thread to be in either P1 or P2 or all the Pn functions, right? If you define the whole thing to be a monitor, then that's all you do, right? You as a user only has control to say what is a monitor, and essentially all the procedures inside, only one of them gets to run, right? It's a little bit tricky because you have to figure out what exactly it's a monitor for, and I'll tell you what that in a minute. But essentially, doing this, you don't have to worry about fine-grained notion of what is critical section. Now you have you lock the whole function. If you want something which is not in a critical section, you move it outside this monitor, and those functions will be run by any number of threads, right? So this means in your program, only one thread can be inside one of P1 or P2 or P3 or Pn, and nobody else, right? And you might have used this in Java, right? Java uses monitors, and Java calls it synchronized. If you call an object synchronized, then all the functions inside them are treated as monitors. How many of you use the synchronized class? I mean, the synchronized keyword for functions? How many of you are like good with Java? You have taken a course in Java, right? Okay. I sound surprised because 2 years back, people only knew Java, didn't know C, and then I think we were switching, so I don't know if we fully got rid of Java, right? So if you use Java, so you said you used Java, right? So have you used the synchronized class? Yeah. Did you use it because the compiler was complaining that you should make some variable synchronized, or did you use it because you understood what was? Okay, that's good, right? So the way you define a class as so you define the whole class as synchronized, right? And if you don't know Java, right, bear with me, but essentially you have the whole you call the whole class as synchronized, right? So it's not the function which is synchronized, but the enclosing object, right? So it's not. So if you create two instantiations of this object, right, if you like for example in this case, if monitor 1 happens to be one object, if you have two instances of this object, if you do object 1.p1 in one thread and object 2.p1 in another thread, they can still run concurrently. Does that make sense? Hang on, let me look at that. Suppose you have a sort of a construct like this, right? This is synchronized object, right? And you say you create two objects, right? In abstract notion, right? So if you say obj.func1 Oh, sorry. Does that make sense? So you're not making the monitor. So here you had a function definition, right? It's not. So you're creating a monitor for this entire object, right? You made the entire object synchronized. That means the object 1 and object 2 are different objects, right? So this would be fine if the object only operated on the local variables of the object 1 and object 2. So if func was operating only on the local variable for the object, you're fine. But object.func and object1.func can both be running concurrently because the monitor is on the object, not on the function name. Does that make sense? But regardless, you have to make sure that you understand what exactly the monitor is protecting, right? It may or may not be the function name that you're thinking. It might be the part of whatever, because what conceptually happens is internally you may replace the function, the whatever monitor you have, with the binary lock or what have you, right? But once you understand this concept, it's much easier to program, because essentially, if you think that two functions are operating on a single variable, you can define both of them as monitors, right? You lose the control of fine-grained stuff, but essentially only one thread can be in either P1 or P2. So if P1 and P2 happen to be operating on the same shared variable, then this will give you the same functionality as worrying about monitors, and still make your program easy to program, right? There's a lot of discussion whether this actually is what we should be doing, right? But this is one way of getting the goal, right? You may think monitors for your project, but in all likelihood, you may find that monitors are too restrictive for what you're trying to do, right? If you want to see a sort of linear increase in speed, having monitors may be a blunt equipment, right? It may have to block the whole matrix. If you want to do a fine-grained control, you may want to get the control sort of like a semaphore or what have you, right? But essentially, you implement internally a monitor by putting a semaphore or lock for every function. Beginning of the function, end of the function would achieve the same thing as a monitor. But the nice thing is you can do this without knowing anything about synchronization, so the story goes, right? If you write Java programs, sometimes it'll complain and say you have to make some of your objects synchronized, and this is what it's essentially trying to do. So let's see how we can implement the dynamic philosopher's problem using monitors, right? Remember the dynamic philosopher's problem, right? There are 5 people sitting around, and I think in the next lecture or so we'll see why that 5 is an important number and not, say, 4 or something, right? But essentially, you have 5 philosophers sitting, and they want to eat some food. They need the left and right fork, chopstick, or what have you, and they have to have both of them to eat the food, right? If they can't get both of them, then they have to wait for somebody, right? So one way to solve the problem is through this little code segment, which we use using monitors, right? Since we call this a monitor, that means only one of them can be inside. So let's assume there are 5 philosopher threads, right? Those 5 philosopher threads, only one of them can be making the decision whether to do any of these functions. And you avoid the synchronization problem that way, and you still solve the dynamic philosopher problem, right? In order to understand how this works, let's go to the next slide. First, the main function here is the test function, right? The test function tries to see if philosopher I can eat, and if they can eat, then it changes the state to be eating, right? So we have an array called state for each thread. It can be either in thinking, hungry, or eating, right? So when the philosopher is thinking, when they don't want to eat, they'll be in thinking state. When they want to eat, they'll be in hungry state, and then when they're actually eating, they'll be in eating state, right? So what the test function does is, if you are a thread I, or a philosopher I, you look to see whether you are hungry, right? You look to see whether you are hungry. You look to see if the person on the right is eating, if the person on the left is eating, right? If the person on the left and right are eating, that means they have both the forks. That means they have the fork that you want, right? I want the left and right fork. If the person on my right is eating, that means they have the fork on my right. That means I cannot do anything, right? But if the person on the right is not eating and the person on the left is not eating, then, right? So essentially, you take your state and then you add 4 and then mod 5. That means you go back 1, right, in a circular list. So you look to see if the person on the left is eating. You look to see whether you are hungry, and it'll be clear why you want to do that. And then you look to see the person on the right, which is the state plus 1 mod 5, right? So you look to see if all the three are, both the ones are not eating and you're hungry. If you are, then you change your state to eating, right? So that means now you are eating, and you send a signal, right? You send a signal so somebody else can wake up, right? So that's the meat of the function, the way the program works. So there are two operations. One is put down, and one is pick up, right? Pick up is when you want to eat, you want to pick up the fork, right? If I want to pick up a fork, I first try to change my state to hungry, because I need to be hungry to start eating, right? And then I do a test for myself, right? So I want to pick up, I want to start eating. So I want to see if I can eat. So I set the state to be hungry, myself to be hungry. Then I run this code, right? So if it turns out that both my left and right are not eating, that means in the code, how to change my own state to eating, right? And that means I picked up the code, right? I picked up the fork. But if after testing I come out saying I'm not eating, that means either the left or the right was eating, right? If you look at the test code, for this to fail meaning that it will return with whatever state of the thread I was, which is hungry here. You will either have to have the left or the right to be in eating state. If one of them was in eating state, you'll return back with your own state being hungry, right? If your own state was still hungry, meaning not eating here, you put yourself on wait, right? So if you want to start eating, you look at the left one, you look at the right one. If they're not both eating, then you can put yourself into eating state. Then you fall through. Then you fall all the way out of this. But if it turns out that one of them is eating, then your state will still be hungry. So you put yourself in wait, right? So hopefully, when one of the thread finishes, right, they will signal back to you so you can get to eat, and we'll see how that works, right? So put down means that once you're done with your eating, you want to give up your CPU, you want to give up your forks. The way you implement that is you change your state to thinking, so you're no longer eating, and then you test to see, you do this test of the left and right, right? You're not really testing here to see what the state is. You're trying to give them control to run, right? So suppose, let's look at one of this case, right? Suppose you're finished eating, right? And you want to do a test of the right one, right? So thread 4, you want to see if thread 4 can run, right? Sorry, if a thread 4, you want to see if thread 5 can run, right? So you call this, right? So you're not really testing to see the state. Your state is now thinking, right? So if thread 5, right, which is what you called on, would look to see what its state was, right? If thread 5's state was hungry, that means it was waiting on some queue, right? And thread, the previous one, which happens to be you, not equals eating, right? Which is true because you set it to thinking, right? So if your next thread happens to be waiting, hungry, in a hungry state, that means it's hungry, you are thinking. So it now depends on what the other thread, the neighbor of your neighbor thinks. If all that also happens to be thinking, then that means you'll go into waiting state, right? So essentially what you do is after you're done, you kind of see if your neighbor wants to eat, and if they want, you let them go, right? So the previous test case, these two cases, the name is kind of misleading, but essentially they give opportunity to say, I'm done with my food, now you get to control, now you get to go, right? Did that make sense? I strongly encourage you to run through this at your leisure, but essentially you're trying to make sure that you let all these things run, right? And all of this works because even though you're operating on the shared state variables, it works because since you made it a monitor, only one of them can be run inside this any function at any one time, right? So it's not possible for one thread to be running pick up and one thread to be running put down, right? Because you can only do one or the other because of the way you used monitors, right? Right? So, yeah, I want you to go through and try to see if you can understand this stuff. Essentially, that's what you have to do for the programming project. And essentially, that's what happens with these kind of synchronization variables, right? You can either have a very, very simple and naive approach where you implement this, where when you're done with your food, you leave the fork, you leave both the forks around, and then figure out something will happen. But this solution kind of, like once you're done eating, you try to see if the right or the left one was also waiting. If they are, you kind of pass the baton to them so they can keep running, right? But so this is some of the ways you would translate your notion of the dining philosopher into programming code, right? Of course, there are a lot of other ways to do this. If you notice, there's actually no concept of a fork at all here, fork or chopstick here, right? It's basically the state variable, but you implement what what you really wanted, right? So in initialization code, you try to make all of them into thinking state, and you let this program run, right? So try to understand what this program does, because that's sort of where the things comes in, right? So when you try to code this into real program, you'll notice that things are not as trivial as you might have thought from the initial lectures, right? The critical section, it looked like you just make a lock here. I mean, you have a begin critical section, end critical section kind of thing. But in this particular piece of code, the critical section conceptually goes where if I want to put down, my critical section goes from there for me to test what my neighbor wants to do. If my neighbor was also hungry, then essentially my critical section goes from me to my neighbor, and the critical section end would be in their thread. Did that make sense? The way we implement it here would be I finish eating, right, in the put down. In the put down case, right? If you were to do this as a critical section conceptually, it starts here. I finish eating, right? And what I'm doing here is I'm trying to see if my neighbor also wants to eat, because I'm done. If my neighbor was hungry, and if my neighbors, both the left and right neighbors, were thinking, then they can run, right? So conceptually, I'm giving control of this critical section to my neighbor, right? So they can, in their thread, continue to run, right? And you will end up seeing many code like that, where the critical section is not a simple begin and end, but conceptually it flows from one thread to the another, because your logic makes it complicated, right? So it's a fair question to ask, how would you implement blah using foo? How would you implement reader-writer locks using Semaphore? How would you implement reader-writer locks using monitors? How would you implement some things using something, right? I think the book has exercises talking about how you do that. Try to go through some of them, because that gives you a sense of how precisely these things operate, right? And again, the key thing to remember is you have to, whether you like it or not, you have to worry about these things, because that's where the modern architecture folks are taking us, right? So if you want to use any other machines, you have to worry about this stuff, right? And I think one of the other things you realize is once you do this kind of exercise and you look at PowerPoint, and it has like 57 threads or something, which is what I saw on my Mac PowerPoint, then you have a new respect for how complicated the code becomes, right? Because what you have to think is not just, if you're used to thinking a program as a straight line of this is what my program is doing kind of stuff, now you have to in your mind have this like 57 little things running, which are all operating on the same shared data. So you have to say, okay, I'm modifying this here, right? I'm done in this thread, but essentially I'm trying to see if my neighbors are hungry. I'm going to turn control over to them. So when this finishes, my thread will continue to run, because at this point it can continue to run because it's done eating. But the offshoot is the other thread, my neighbor thread, will also get to eat, because now they have the food, right? Potentially, at the end of this code, you can have two threads started along with you because your right neighbor and the left neighbor now gets to run, right? And debugging and thinking about those code is not a trivial task, right? So it's kind of weird because this is not exactly operating systems, but it's kind of operating system because no other class will actually go through that concepts. And if you have any questions about this, which is not, if you don't want to bring it in the class, send me email or whatever, and I'll try to answer those, right? And we'll continue with the deadlock and starvation and stuff on the next lecture. Again, drop by and pick up the quiz because I need to know who got the grade.